Okay, welcome. I'm Chuck Hages from the University of Florida. And, first I need to thank the organizers for inviting me to give the talk. We've got a really cool project going on doing machine learning for accelerated analysis of TRPL data. So hopefully some of you are familiar with TRPL. This is a really powerful measurement technique where we just excite photoluminescence or excite electrons in holes with a pulsed laser. We measure their photoluminescence as a function of time. Here's a typical data set from TRPL. The PL intensity is a function of time. And there's really a lot of physics underneath this TRPL data. It's a very powerful technique. It's all optical, so you don't need to make a device to extract material parameters. You can vary the measurement conditions in many different ways to change and extract different information. But in reality, this is wholly underutilized data. Okay, so a typical TRPL scan, maybe you go to high injection and you measure the radiative emission, or you go to low injection and you say there's an arbitrary lifetime. Maybe you justify what that lifetime is, maybe not. But the idea is there's a lot of physics underneath here that is really hard to unpack. Okay, so I want to talk about what information lies in a TRPL measurement and why it's underutilized. And so, here's typical transport phenomena which describe a TRPL. Okay, so our electron and hole continuity equations with drift, diffusion, recombination. Poisson's equation couples the movement of electrons and holes together. We've got boundary conditions for surface recombination, absorption profiles for the different laser wavelengths you use. And the idea is, there's maybe 8 or 10 really fundamental material parameters that are outlined here. They're highlighted in red, which determine this transient electron dynamics. And this is what we want to probe. If you can get this information, you can predict device performance, you can design solar devices. And it's not unique to TRPL. This could be from any measurement. For TRPL, these equations are really integrated to give you, an integral PL signal. So it makes it even trickier to decouple all the underlying physics. And so, typically what happens is when you want to do analytical analysis, we have to find these limiting regimes. Okay, so maybe we go to high injection and we assume only radiative recombination matters. So we can take this equation, ignore everything else and solve an analytical solution. Okay, typically that can't be done. The full drift diffusion equations are partial differential equations, nonlinear, coupled. And so if we can find these limiting regimes, we fit analytical solutions. Maybe you do the same for, shock with Reed-Hall recombination in a given regime. And the idea is, I did a lot of this during my PhD and my postdoc, and after it's a lot of manual analysis, a lot of manpower, and a lot of really approximations that go into being able to tease out specific parameters in unique ways. And it really begs the question, why are we analyzing data manually? Okay, so really, this is the era of quantum computers. So, there's enough computational resources out there that don't even come to this level where we can, improve the way we do this data analysis. And this is what we're applying to TRPL data here. Okay, so I want to give you an overview of how we do our analysis. This is a statistical analysis. So you can take a look at this black curve. This would be a typical measured TRPL curve. And what we do is we compare this measured data to millions and millions, maybe 10 million simulated curves. All these blue curves would be simulated data. And this simulated data has to span this 8-dimensional parameter space. And what we want to find is for each simulated data set, what's the likelihood that it describes our measured data. Okay, so this is Bayes' theorem. So we apply Bayes' theorem, and we build a probability for a given parameter value based on the known probability and the likelihood of the data that you're computing at a given point in time. So this likelihood is a Gaussian distribution. It's really best if I just show this video probably. What we do is we feed data into the system, and we can build confidence on particular values that have high probability to describe our curve. Okay, so we do this is iterated. So the computer is continuously adding new data to improve our probability histogram. Now, this is not one-dimensional. This is kind of an oversimplification. In reality, we're doing this in a multi-dimensional iteration. And so we're simultaneously inferring many parameters because we're sampling this huge parameter space with our simulated data we're comparing to. And this is far superior to analytical fitting of curves, because you can't fit 8 parameters with an analytical equation. I mean, you'd be overfitting the data. So we can do that with a statistical analysis. And yeah, I want to show you a case study. So let's take an arbitrary photovoltaic absorber. We have a power scan data set from TRPL. And we feed this to our Bayesian Inference algorithm. And this is a simulated data set. We overlay some experimental noise. And it's simulated because we have known input parameters. So we can, when we infer, we can determine if we can accurately extract these values that we know they have to be. And this turns out to be a really powerful technique. Okay, so in this case, we've got equal mobility, low surface recombination, and we can infer 6 out of 8 parameters that we're inputting to this transient simulations. And this is a significantly improved information density from TRPL analysis. So we're really happy with this result. I mean, I just showed you we typically get 1 or 2 parameters. Okay, so we can really get a large number of parameters from just a typical data set. We get high accuracy of these parameters compared to experimental fitting. We don't have to go to these narrow regimes where certain terms dominate. So you can see this with these error bars. We get much better data because these values that I'm showing in this table are based off of probability histograms. Okay, so these, for example, look at the doping. So the red value is our known input value. And what we do is we sample all this space of possible dopings, and we build a probability as these blue lines. So the peak in the probability histogram is in excellent agreement with our known input values, and we get a confidence on a given parameter. Okay, so this is also tricky to get with analytical analysis. And so, you can see we get pretty good confidence. At least we get the information about confidence on our parameter inference. We get parameter correlations on I'll talk about this in more detail, but we get the relationship between parameters, which are hard to decouple, which you really can't get from analytical analysis without knowing the underlying physics, the solutions really well. And we can design better experiments. Okay, so when we're comparing millions of simulations, we can really do how can we better change our measurements to improve the confidence in extracting certain parameters. So I'll show you this for distinguishing electron and hole mobility and front and back surface recombination, which is actually a really unique thing to do with TRPL data. So I'm not gonna, in the interest of keeping your attention and time, I'm just gonna talk about a few things. I'll talk about mobility, surface recombination. The rest is gonna be in our publication that's coming out. And these are great examples on kind of how we do a physics-driven analysis, okay? And so mobility in particular is a nice one to talk about because there's a lot of underlying physics you need to understand to accurately infer this value. And so this is the simplified transport equations for our case with equal mobility, low surface recombination. This would be kind of the transport equations in high injection. And we also, well, the idea is if you want to get carrier mobility, you need to find, where does that dominate the electron dynamics? And it really dominates this term here. This is our diffusion flux or diffusion current. So we need to go to a region of the data where this term is important. And this happens when you have a large gradient in your electron profile. So indeed, this occurs at early times. So when you pulse a laser onto your sample, we initially get this exponential profile, a Beer-Lambert absorption profile. These are our electron profiles at different times underneath this TRPL curve. These are simulated. And so the idea is there's a certain time constant where these carriers are diffusing to become uniform, and they want to lower their chemical potential. And then after a certain time period, we'll call it tau d, diffusion time. We call it quasi-equilibrium decay. And at that point, the carriers just decay uniformly according to these recombination terms. Okay, so if you want to sample mobility and understand the impact of mobility, we need to probe data in this carrier redistribution regime. And we can solve this. This is just a simple Fick's law diffusion. You can get a characteristic diffusion time. For this particular absorber, this would be about 8 nanoseconds. And this is based off of a real material. This just happens to be simulated. But, okay, so this is what we do. We need to probe data during this diffusion time. And this is exactly what we do. If we feed in data up to this red line during carrier diffusion, we get a fairly accurate inference of our mobility, or the equal electron and hole mobility, about 20 centimeters squared per volt second, with good confidence. But what happens is, as we add more data, for example, maybe we go to 200 nanoseconds and we feed more data into our inference algorithm, the confidence in inferring this parameter decreases. And actually, if you feed in the entire data set, there's very poor, you don't have any ability to infer the mobility. And so your confidence is really diluted because all of this data at later times, this is during this quasi-equilibrium decay, where mobility is not important on the data. Okay, so we're diluting the data by including data which doesn't have any relationship to the mobility. And so you need to understand which regimes are important. So this is kind of what I'm trying to get at, is this is driven by the physics, okay? So you need to understand which regime of the data is going to give us the important information. And so we actually do a two-stage inference. We analyze the data at early times for mobility, and then we fix the mobility, and then we analyze all the other parameters with the full data set. The carrier redistribution doesn't just have to occur, but it has to affect your data that you're measuring. Okay, so you have to have an impact on the PL data. And so, for example, this is the PL data during carrier redistribution. We see there's a big drop in the initial PL data. And, this red dot is t equals 0. You have this exponential profile. Let's assume there's no recombination essentially during this short time period. The second red dot is at the diffusion time. So now everything's become uniform. So it's the same carrier density, but one's a profile and one's uniform. So if you compare the PL ratio, if you just compute it analytically at these 2 points, in high injection, what you see is that you're always going to have a drop in your PL signal. It's always going to be less than 1 when you're measuring a uniform profile compared to an exponential profile. So this is what we call a diffusion hook. It's purely due to carrier diffusion. Your PL changes intensity not due to recombination, but just due to diffusion. This is good for us if we want to measure mobility. In low injection, for example, this doesn't happen. Okay, so if you were trying to measure this, you could have insane carrier profiles. You could do whatever carrier profile you want, encourage diffusion, but you're not going to measure it in the PL data because it's monomolecular decay versus bimolecular decay. And so the point is, it's still physics-driven analysis. So you need to understand we have to put, your PL depends on the carrier profile and high injection. So we have to feed high injection data that happens to be during carrier redistribution. And the mobility gets even more complicated. So, this is the fixed Fickian diffusion of electrons and holes if you have an equal mobility. But the exact same diffusion would occur if electrons and holes separate and, they're charged particles, so they're pulled back together by an electric field. And so, they can travel, if the electric field is strong, as a single particle with ambipolar mobility. And this is our simple ambipolar mobility term, which would fit into the same diffusion equations that we just talked about. So in high injection, this simplifies to a very simple relationship between the electron and hole mobility. And so, if you don't know that the mobilities are equal, you actually can't learn that information. And so, for example, if we put in an equal electron and hole mobility and you infer them independently, this is the 2D probability histogram for electrons and hole mobility. And what you see is that, all of the high probability points lie along this curve. There's not a single point. And this curve, this black line, is described by this equation. Okay. And so what we do is we infer a parameter correlation between the electron and hole mobility. And this correlation, we know the physics can be described as an ambipolar mobility. But you don't have to put any of this analytical assumptions in. This parameter correlation is something that we extract from the data. So I'm just using it here to describe it because it's a simple case where we can describe it. So these parameter correlations are really useful to be able to extract, especially for more complex films. For example, what if you had different mobilities? So what if your electron mobility was 60 and your hole mobility was 12? So in this case, you have the exact same ambipolar mobility of 20, and your curves look exactly the same. And so you'd get the same ambipolar mobility, but you can't distinguish with any confidence what the real electron or hole mobility is. So this is kind of the importance of these parameter correlations that we get out from statistical analysis. So this is kind of a good overview. I mean, the mobility is a good one because there's a lot of overlaying or underlying physics to decouple. But another parameter would be our Shockley-Reed-Hall or non-radiative lifetimes. This is a very common parameter. Maybe you get an exponential decay in low injection. And really, it can be bulk or surface recombination in high or low injection. And the problem is these are all linear with the carrier density. Okay, so you can't distinguish them. So, you get an effective recombination rate or lifetime, which is bulk and surface contributions. And so this is what we infer. We infer an effective Shockley-Reed-Hall lifetime with pretty good accuracy. But if you look at the correlation between the minority carrier lifetime and the sum of the front and back surface lifetimes, we see that actually they lie on this curve. We don't know them independently. They lie on this black curve, which is described by this equation, which is the Shockley-Reed-Hall lifetime. And so we can't distinguish front and back surface, okay? And so this is a way that we can extract parameter correlation, or in this case, it's an easy example, so we know what it should be to kind of give you a proof of concept. And it makes you wonder, what can we do to distinguish, once we know this correlation, how can we change the measurement to distinguish the front or the surface from bulk recombination? So one way you can do this is, you look at this, inspect this effective lifetime. These are two recombination paths that are happening in parallel. And so we can just alter one, and you can change the thickness to affect the surface contribution. So we can add a second thickness. So if we feed in data, power scan data from a second thickness, you can alter this Shockley-Reed-Hall lifetime. You can see the slope changes for the two different thicknesses. All the material parameters are exactly the same. So we're not changing the material. We're just changing the thickness. So the relative contributions of these different parameters. So we can easily distinguish these things now. And so we feed this two thickness data set in, and now this is where we can really accurately distinguish surface from bulk recombination. So you get both of these terms with very high probability. And if we include high injection data, this bulk term would now transition to minority plus majority carriers. So if you include two thicknesses plus high injection, we also get the majority carrier lifetime. And yeah, I mean, this is another example of how you understand the physics to help you figure out what kind of data you need to put into this analysis. It's not a black box. It's physics driven. So this is truly, in my opinion, accelerated TRPL analysis because, we've really increased the ability to get information and the quality of information from a power scan, or maybe a two thickness power scan. And these analytical solutions are just a guide. Okay, so you don't need to know or do any of these analytical solutions. I'm using them as a guide to show you why we can get these different parameters. But the whole power of this technique is that you can have overlying physics. So for analytical solutions, we have to find these limiting regimes and analytical approximations to fit it. Whereas here we can have completely overlapping physics, and it's not a challenge to distinguish these things statistically. And that's the goal. I mean, we don't want to make approximations. So, last thing I want to touch on is being able to design some experiments to really distinguish, which I think is fairly unique for TRPL, electron and hole mobilities or front and back surface quality. So one way you can do this is to probe a sample with high surface recombination. Okay, so what you can do is you can take your absorber after you analyze it, and you can take sandpaper and you can destroy the surface on purpose because we want the surface to be bad. And the goal here is that when we're limited by surface recombination, carriers have a serious process of diffusing to the surface, then recombining. And so if the surface recombination is really high, you become limited by diffusion. We know this diffusion time. This is our characteristic diffusion time. And by causing diffusion to affect the recombination rate at the surface, now we've allowed diffusion to affect the entire curve, not just this really narrow diffusion region at early times. That's kind of the goal. So since diffusion contributes to the slope, it doesn't dominate it. It's just a contributing factor. In high injection, this diffusion time is a function of your ambipolar mobility, okay? And so we said that, the ambipolar mobility will be inferred from the slope in high injection. And in low injection, or if we're below the threshold for ambipolar diffusion, we're actually limited by the minority carrier mobility. Okay, so and that's what you can see here. If you look at the photoluminescence, this is at different minority carrier mobilities, is simulated different curves, and you can see that the minority carrier mobility only matters in low injection. Okay, so if you feed data that has both of these regimes, you get ambipolar plus minority, so you get both minority and majority. And they don't dominate the decay. It's hard to do this manually because you also have surface quality. Okay, so it's just a contributing factor which is simultaneously inferred. Okay, so this is an example for electron hole mobilities. We can also, using the same idea, a high surface recombination, distinguish front and back surface recombination. Okay, so if the surface recombination is really bad or high enough, then during carrier diffusion, these carriers are recombining at the front surface as they diffuse away from it. And so you can solve this analytically as an example. And the front surface is really important at early times. And during this quasi-equilibrium decay, at later times, you get this uniform profile. It's not really quasi-equilibrium when you have high surface recombination. But the idea is both surfaces are important when you have a relatively uniform profile. And so if you include different temporal regimes now for the high surface recombination, now we can sample SF and SF plus SB, so we get both of these terms. Okay, so what we're doing is we're including, if you have a power scan data for something with high surface recombination, you include different injection regimes, different temporal regimes, then we can simultaneously infer electron hole mobility, front and back surface recombination. And these are, in my opinion, really unique values to extract from TRPL, and we get them with fairly high accuracy. And so, of course, there are limits of when you can do this, but it's an example of designing better experiments. So, really, I want to talk about where this is going. So we're currently doing this on a GPU. And so GPUs are highly parallel, so we can run millions of simulations. So, we run 10 million simulation parameter sets in parallel. We use parallel cyclic reduction to simulate individual parameter sets also in parallel across GPUs. So, my student is really phenomenal at being able to program this. It's a highly efficient numerical simulator. But we're just sampling this huge parameter space. So if 10 million simulations, only 0.1% are really effective to build a histogram because all the rest are so unprobable that they don't even contribute. And so we found now, after using these DGX A100s, these really powerful GPUs from NVIDIA, that we could probably do this with CPUs better. And now we can actually do this on a desktop computer. And so we've got a Markov chain Monte Carlo method going, where we kind of in series find these high probability regions, and then we can let the CPUs loose to sample this high probability region only. Here you can see kind of sampling a parameter space. These are 4 different CPU chains all kind of converging really quickly onto a high probability space. So it's a very robust way to do this, and we can apply it to way more complicated simulations now. And we're going to release this code so you can just do this on your desktop computer. And also, I showed you a really simple example where we have an absorber. And to be honest, even a simple example, we can get way more information. But this really becomes powerful when you can't get analytical solutions. Okay, so what if you have devices and you have a complex electric field in the device, which people measure TRPL on devices, and CIGS, you get band gap gradients. We've done some simulations along electron transport down nanowires. So we really want to explore these complex architectures where analytical solutions are impractical. Okay, so you need to use a technique like machine learning or Bayesian inference to analyze your data really practically at all. And you can also design experiments where the analytical solutions are impractical. So what if we want to have carrier diffusion occur across the entire measurement by using an AC voltage on a device? So this is the kind of stuff we're working on. And of course, you're not limited to TRPL. You can apply this to any measurement technique as long as you can build a numerical simulator for the to describe the physics. Then you can use this sort of statistical inference. And they do it for astronomy for a very long time, And also some other techniques for current voltage measurements has been shown. But yeah, the transient measurements, this has been a really challenging problem. But in conclusion, I hope to have shown you an accelerated analysis of TRPL data via machine learning. It's got improved information density from typical manual analysis, much more useful data with histograms and confidence and correlations. It's semi-automated, you have to it's physics driven, but semi-automated analysis. Design better experiments. And of course, in the future, we want to apply this to complex materials and architecture. So this is kind of a proof of concept to hopefully get you excited about the approach. And of course, I need to acknowledge support from the research computing at UF, which gave us access to these really high-powered GPUs. And then now in the future, Sony is funding this project with this Faculty Innovation Award to do some machine learning analysis on their interesting device structures. And with that, I'm happy to take some questions. Thank you.